Hi. It would be difficult to talk about pair production in antimatter without first talking about Paul Dirac. Now, Paul Dirac was a really interesting person. He might be one of my favorite physicists from history, just because he had such an interesting perspective on the world. So he was kind of taciturn. One of his famous quotes, which I believe he said to Niels Bohr, was, "I was taught at school never to start a sentence without knowing the end of it." So he didn't have much to say on certain occasions. He also had a lot of interesting interactions with his colleagues, Oppenheimer and Dirac. A famous story from a quote that he used with Oppenheimer was this: "Oppenheimer, they tell me you're writing poetry. I don't see how a man can work on the frontiers of physics and write poetry at the same time. In science, you want to say something that nobody knew before in words which everyone can understand. And in poetry, it seems to be the opposite." So that's pretty witty. There was also a fun story about Heisenberg and Dirac when they were on a trip to Japan for a conference, and they were on a ship, a cruise basically. And so Heisenberg was a really outgoing guy, and he liked to socialize, and he used to dance with the young ladies on the ship before dinners, and Dirac used to just sit there and watch and stare at him. And so once Dirac asked him, "Heisenberg, why do you dance?" And Heisenberg replied that when there were nice girls, he felt like dancing with them. And that made Dirac think, and so he thought a minute, and after a little while he said, "Heisenberg, how do you know beforehand that the girls are nice?" So that's kind of fun. But he was the Lucasian Professor of Mathematics at Cambridge, and he shared the Nobel Prize in 1933 with Schrödinger for the discovery of new productive forms of atomic theory. Basically what happened was Schrödinger developed the non-relativistic equation, which describes quantum mechanics, which we'll talk a lot about later on in this semester, and Dirac developed the form of the equation that incorporates special relativity. And so Schrödinger published his equation in 1926, and Dirac published his equation a few years later. Now, some of the fallout from Dirac's equation was actually kind of interesting. First of all, Dirac's relativistic equation actually came out with the quantum number of spin, which Schrödinger's non-relativistic equation couldn't do. Now, spin is an intrinsic angular momentum that a particle has. We're going to talk more about that later this semester, so more to come on that topic. But another point that fell out from Dirac's relativistic equation for quantum mechanics was the idea of antimatter. Now, according to the predictions from Dirac's work, for every particle, there should be an antiparticle. So every particle should have a corresponding antiparticle. Now, the antiparticle for the electron is called the positron, and it has the same mass as an electron, but the opposite charge. So one of the interpretations, early interpretations of Dirac's equation for relativistic quantum mechanics postulated the idea of something that came to be known as the Dirac sea. Now, the Dirac sea is a theoretical model of the vacuum, basically a model of nothingness. But in this nothingness, there's actually something, okay? So this vacuum, this nothingness, is supposed to be an infinite sea of particles that has negative energy. In other words, if a particle had negative energy, that meant that it hadn't been brought into existence yet. And all it needed to be brought into existence was to be given enough energy to come out of that bound energy state, that nothingness, that vacuum, and be created. Now, when the electron, for example, is created from the Dirac sea, it leaves behind a hole. Now, Dirac thought that this hole would move in response to an electric field as a charged particle. It would move as a positively charged particle because it's the absence of a negative charge, if that makes sense. Now, at first, he wasn't really sure whether this positively charged particle would be a proton or what it would be, but Oppenheimer later came in and said, no, it has to have the same mass as its corresponding particle. And so the idea of a positron was born. It was later confirmed experimentally a few years later in 1932 by Carl Anderson. But Carl Anderson's work wouldn't have been possible without the foundations for the theoretical and the experimental foundations laid by Victor Hess, and Victor Hess studied cosmic rays. So in a series of experiments in the early 1900s, Victor Hess took balloons up to different altitudes, higher altitudes. And what he was doing was he was measuring the amount of ionizing radiation at these high altitudes. He then compared the amount of ionizing radiation that he found at these high altitudes with the amount of ionizing radiation at sea level, and he found that the levels were much, much higher, as much as 3 times higher as sea level. And he had discovered basically cosmic rays. Now it turns out that cosmic rays are high energy particles, mostly protons, that come in from outer space, and then they collide with atoms in our upper atmosphere, or nuclei in our upper atmosphere. When they do that, they create other particles, like pions, which decay into muons, or like radiation, for example. And then those particles can be detected here at the surface of the Earth or in Hess's balloon experiments. Now, one of the early ways that they used to detect particles was by a cloud chamber. Now, C.T.R. Wilson perfected the design for a cloud chamber and later won a Nobel Prize for that work. And this was in the early 1900s. Basically, a cloud chamber is a vacuum chamber which has been backfilled with originally water vapor. And then what happens is when an ion or a charged particle interacts with the vapor inside of the cloud chamber, it causes the water in the path of the ionizing radiation to condense and leave behind a visible track. These tracks could then be photographed. So this is a picture of C.T.R. Wilson's cloud chamber, or a facsimile thereof, from the Cavendish Museum. Now, if you have these cloud chambers and their later cousins, bubble chambers were used in the 1950s and 60s in particle physics research, so they came later. But if you put a cloud or a bubble chamber in the presence of a strong magnetic field, then any charged particles that are moving through the cloud or bubble chamber will make spirals, okay, and leave interesting tracks behind. Now, if you have a particle-antiparticle pair, their charge is going to be opposite. Now, according to Lorentz force law, F is equal to QV cross B. So what that means is that a positively charged particle will make a circle in the opposite direction to a negatively charged particle. And that's shown here in this picture of a bubble chamber event that I took from the CERN website. So in this bubble chamber event, it shows the creation of a positron-electron pair, and that's those linked spirals right there that will move. Of course, this is the path made by the positron and the electron in the presence of a magnetic field, and they spiral inward because all the time they're losing energy. Okay, so Carl Anderson used a cloud chamber in the late 1920s, early 1930s in his research. And he sat around basically and waited for a cosmic ray to interact with his cloud chamber vapor and leave behind a track. And he discovered in 1932 the first ever report of the track of a positron from a cloud chamber. Now later, he went on to confirm this work and do a better experimental verification, getting a lot more data, by using a radioactive source to generate his gamma rays, rather than sitting around and waiting for an event to happen inside of this cloud chamber from a cosmic ray. So he got a lot more data that way. And the cloud chambers got a lot more sophisticated as time went on. You can see Carl Anderson here at Caltech with one of the later generation cloud chambers, and he generated really strong magnetic fields by surrounding the cloud chamber in coils of wire, creating strong magnetic fields inside the cloud chamber. So a lot more work was done. He also discovered the muon. They were looking for the pion. We'll talk more about that in modern physics too. And then when they found the muon, reportedly one of the particle physicists that read the paper or heard about it said, "Who ordered that?" So that's kind of funny. But anyway, back to pair production. That's kind of the history of pair production in antimatter. So now let's talk about the actual physics of it. Now, of course, a common source of positrons is pair production. Pair production is defined as when a gamma ray photon with sufficient energy interacts with a nucleus and then creates an electron-positron pair. By interact, all I mean is that the gamma ray has to pass near enough to the nucleus to transfer a little bit of its energy and momentum to that nucleus. And if that doesn't happen, you can't get pair production, for example, in empty space. Now the amount of energy that the photon has to be really high, because energy must be conserved. And so the initial energy of the photon has to be at least equal to the rest mass energy of the positron and the electron that are created. So that's going to be 2mc squared to create the pair, where m is the mass of the electron. And of course, it has the same mass as the positron. Now, pair production can be done quite efficiently if you shoot your gamma rays at something like a lead plate. And then you can see, this is an image of some experimental production of positron and electron pairs. You can see that a lot of them are created here. You can see at least 3 there in the tracks. All right. So here you have 300 MeV gamma rays striking a lead sheet and then creating these positron-electron pairs that are shown as these paths that move off in opposite directions in the presence of that strong magnetic field. Now, as I said, this can't take place in empty space. And let me explain why. So first of all, in all of these particle physics interactions, you still have to go back to physics 1150 and conserve energy and momentum. Okay, those must be conserved. So let's talk about what energy and momentum conservation might look like if pair production took place in empty space. So first of all, your photon energy, which we know is hf, where f is the frequency of the photon and h is Planck's constant, hf has to be at least equal to the rest mass energy. But let's assume that we give it a little more than that it gets some energy, a little kinetic energy too. So then hf has to equal to the total energy of your electron-positron pair. And that would be 2 gamma mc squared, okay? I'm going to assume for the rest of this slide here that the electron and the positron that are created have equal momenta, okay? That they're symmetric with respect to one another. So in other words, the speeds of the electron and the positron should be the same, and so the value of gamma should be the same for both the electron and positron. That makes the total energy for the electron-positron pair 2 gamma mc squared, if we use the equation gamma mc squared for the total energy of a particle. Now, we also have to conserve momentum, okay? Now, the momentum of a photon is its energy divided by the speed of light, E over c. So that reduces to hf over c if we plug in E is equal to hf for our energy of our photon. And that has to equal to the final momentum of the system. Now, if you assume that the electron and positron move off from the original path of that photon at equal angles from the original path theta, then the momentum, the relativistic expression for a momentum of a particle is gamma mv. Then the total momentum of the final system in the x direction would be 2 gamma mv cosine of theta. All right? Okay, so we can then take that expression for the momentum, multiply both sides by c, and then we'd have hf is equal to 2 gamma mvc times cosine of theta. Now, I want to do that so that I can relate the equation for conservation of momentum to the equation for conservation of energy. So now I'm going to see if these two expressions for hf give me something that I can set equal to one another. So here I have 2 gamma mvc cosine of theta equal, question mark, to 2 gamma mc squared. And we see that it's actually not possible to set these two expressions for hf equal to one another. Okay? The 2 gamma m cancels out, but then we're left with vc cosine of theta equals, question mark, c squared. And of course that can't be the case, because nothing with mass can travel at speeds equal to the speed of light, so v must be less than c. And then also you have that cosine of theta term, which is going to be a value between 0 and 1. And yet, so you see that vc cosine of theta has to be less than c squared. And so we can't simultaneously solve the equations for conservation of energy and momentum if that gamma ray decays in empty space into a positron-electron pair. So this is our contradiction. So in pair production, the simultaneous conversion of energy and momentum in empty space is an impossible situation. And in fact, what you have to have is a gamma ray passing through matter, okay? So what happens then is the gamma ray photon, as depicted in this cartoon, passes near to a nucleus, and then some of the energy from that photon gets transferred to the nucleus, and it gets a little kick. and this helps satisfy energy and momentum conservation. Now you can't know exactly how much of a kick that nucleus is going to get. It doesn't necessarily need much depending upon the final speeds of the electron and the positron and what those angles are, okay? But we do know what the minimum energy for pair production would be, and that's setting the kinetic energy of the whole system equal to 0. And so we know that the minimum energy would be HF equal to 2mc squared, and so HF must be greater than that in order for pair production to happen. So for a positron-electron pair, the minimum energy that your gamma ray photon can have is 1.022 mega electron volts, because 0.511 mega electron volts is the rest mass energy for a positron and an electron. Now, the reverse of pair production can also occur. Basically, if you have a positron and it's anywhere near matter, it's going to see a lot of electrons. Now, there's going to be an attractive force in between your positron and your electron, if for no other reason than just because the positron is positively charged and the electron is negatively charged, and they would be attracted to one another via the Coulomb force, okay? So they get pulled together by that Coulomb force attraction, and then as they get pulled together, they recombine and form, you guessed it, photons again, okay? So this can happen in empty space, by the way, and still satisfy conservation of momentum and energy. Now, oftentimes in high energy particle physics and in nuclear physics, we borrow the notation that chemists use, okay? So here, this reaction is shown as E minus plus E plus yields 2 times gamma, where E minus is the symbol for the electron, E plus is the symbol for the positron. The plus sign shows them recombining, yielding, that's the arrow, 2 gamma ray photons, okay? So a kind of cartoon of that is depicted here. Basically, a positron passing through matter is likely going to annihilate with an electron. It's drawn to an electron by that mutual electric attraction, and then the electron and the positron form an atom-like configuration that's called positronium, which is a pretty awesome name, by the way. Now, what happens is the positron and the electron start spiraling in together, okay? So they're sort of orbiting one another, but they're being pulled in closer and closer until they get so close that they just, boom, recombine, okay? Now, because they have to conserve momentum, if you start from sort of a situation where they're circling one another, then what you have to have in order to satisfy conservation momentum is 2 photons, not just 1, but 2 photons, that then move in opposite directions to satisfy momentum conservation, okay? And they would have an energy HF1 and HF2. So via conservation of energy, 2mc squared has to be approximately equal to HF1 plus HF2, and conservation of momentum says they have to move in opposite directions, so 0 is equal to HF1 over c minus HF2 over c, okay, so they're moving in opposite directions there. They're going to be almost identical, so their frequencies are about the same. And so that means that each photon has an energy equal to the rest mass energy of a positron or an electron, which is 0.511 MeV. And that's if basically the speeds of the positron and the electron are really slow. Now, I'd like to do an example problem where the speeds of the positron and the electron are not so slow. So here my example problem is, an electron and a positron are moving side by side in the plus x direction at half the speed of light when they meet and annihilate one another. 2 photons are produced that move along the plus x-axis, or move along the x-axis. Do both photons move in the plus x direction? In other words, are they moving in the same direction? And what's the energy of each one of those photons anyway? So if we're going to solve this, let's use momentum and energy conservation to do that, okay? So for the initial speeds that we have in this situation, we've got to calculate gamma, because half the speed of light is moving along at a pretty good clip. So gamma for half the speed of light is 1.155. Remember that gamma is 1 over the square root of 1 minus v squared over c squared. Now the initial energy of the system is the energy of the positron and the electron together. Now they're moving at the same speed initially, so basically you can set their energies equal to one another, gamma mc squared for both, and you have 2 gamma mc squared for that initial energy, 2 because there's 2 particles moving at the same speed and in the same direction. So gamma is 1.155, and then the rest mass energy is 0.511 MeV for both the positron and the electron. And if you multiply 2 times 1.155 times 0.511, you get 1.18 MeV for your initial energy of your system. Now this has to equal the energy of the system at the end, which would be the energy of the 2 photons, HF1 plus HF2. So that's our energy conservation equation. Now our momentum conservation equation is made a little simpler because all motion is on the x-axis, as it says in the problem. So we're not sure if both photons move in the plus x direction or not, but we can set the initial momentum equal to the final momentum and solve for that. So our initial momentum is 2 gamma mv, okay? All motion's on the x-axis, so I've dropped the I hat and the j hat unit vectors here, and I'm just talking about it as a plus or minus sign for plus x or minus x motion. So 2 gamma mv yields 2 times 1.155 times 0.511 MeV per c squared, that's the rest mass, times the speed, 0.5c. When you multiply through by all of that, you end up with 0.59 MeV per c for your initial momentum. Now this has to equal the final momentum of the system. The momentum of the 2 photons that are created, you get via the equation hf over c. So the 2 photons momentum would be hf1 over c and hf2 over c. Now we know that this is in the x-axis somewhere, but we don't know if that second photon is moving in the plus x direction or the minus x direction. So I've indicated that with this little plus or minus symbol here because we don't know which is which. I'm just going to assume arbitrarily that at least one of them is moving in the plus x direction. If it's not, I can always rotate my axis so that that's the case. So here I have hf1 over c plus or minus hf2 over c is my final momentum for the system. So continuing along with that solution, my energy equation gives me 1.18 MeV is equal to hf1 plus hf2. Let's take our momentum equation and multiply it by c so we can combine our energy and our momentum equation and see what's happening here. So when we do that, we end up with 0.59 MeV is equal to hf1 plus or minus hf2. So now it's decision time. We have to figure out if we're going to add or subtract here. So to do that, I'm going to compare my momentum equation with my energy equation. Now, I'm going to see here that I can't simultaneously have 1.18 equal hf1 plus hf2 and 0.59 equal hf1 plus hf2. That just doesn't make any sense. And so I conclude that one of the photons has to be moving in the minus x direction, else I'm not going to be able to simultaneously solve this system of equations. It just won't work. So what that means is I've got 0.59 MeV is equal to hf1 minus hf2. Alright, so this is the system of equations that I have to solve. In order to solve for the energies of the 2 photons, I'm now going to add my energy equation and my momentum equation together to solve. When I do that, the hf2 and the minus hf2, they cancel each other out, and I end up with 2 hf1 equals 1.18 plus 0.59 MeV, which is 1.77 MeV. And so now I can solve for what the energy of photon 1 is, and that would be 0.885 MeV. I now plug that energy of that photon back into my energy equation, and I end up with 1.18 MeV minus hf1 equals hf2, and I get 0.295 MeV for photon 2. So that enabled me to solve for the energies of my 2 photons. Alright, so that's pair production, basically. You have a gamma ray photon that then decays into a positron-electron pair, or any other antimatter pair for that matter. It's just that electrons and positrons have a pretty low mass, and so it's easier to create them than it is to create a higher mass particle-antiparticle pair. So it's more common. Now we've covered 3 different ways in which photons interact with matter and display particle-like properties in all of these interactions. The first that we covered was the photoelectric effect. And that was when you have an ultraviolet photon basically striking a metal surface and freeing an electron, called a photoelectron. We had the Compton effect, okay, where an X-ray scattered a off matter. And then we had pair production, where a gamma ray photon basically decayed and became a positron and electron pair. Now, you might wonder which one of these three interactions is dominant, and it depends upon two factors: the energy of the photon itself and also what type of material it's interacting with. That's shown here in this plot. On the vertical axis, the atomic number of the absorber is plotted, and on the horizontal axis, the photon energy is plotted. Now, what kind of atomic number is maybe a little bit more complex than I'd like to get into in this lecture, but you can clearly see that there's an energy dependence here. For lower energy photons, like ultraviolet photons, the photoelectric effect is dominant. For sort of X-ray photons, middle energy photons, the Compton effect is dominant. And then for high energy photons, pair production is dominant. You might be wondering, kind of as we come to the close of this chapter of our textbook, what is a photon anyway? Because all these interactions that we've talked about in this chapter summarize particle properties of photons. But we also know that light is a wave. So how do we wrap our heads around these two seemingly separate ideas? What is a photon? Well, we can talk about its properties. Photons move at the speed of light, 3 times 10 to the 8th meters per second. They have no mass. Mass is equal to 0. Their energy is described as hf, where h is Planck's constant and f is the frequency. And they have momentum, E over c, or hf over c. When they interact with materials, they interact with matter as a particle, and they can be created or destroyed when radiation is emitted or absorbed. One popular way that people have to wrap their heads around the idea of light as a particle is to visualize a wave packet. Okay? So this is a wave that's sort of localized in space and time. And it might have a mental picture that looks like this. But there's no way of getting away from the idea of wave-particle duality. Some experiments are best explained by the photon or particle model, like the Compton effect, pair production, or the photoelectric effect. And some are best explained by the wave model, like diffraction and interference. The idea and the trick is that we have to accept both models and admit that the true nature of light is not describable in terms of any single classical model, but rather some combination of the two. Now, this is difficult conceptually, but there's a nice quote from Crane's Modern Physics that I think sums up the idea of how to do this. Light is not either particles or waves. It's somehow both particles and waves, and only shows one or the other aspect depending upon the kind of experiment we're doing. Our failure to classify light as either particle or wave is not so much a failure to understand the nature of light as it is a failure of our limited vocabulary to describe a phenomenon that is more elegant and mysterious than either simple particles or waves. So I'm going to leave you with that. I hope you enjoyed the lecture. As always, if you need to go back and review something, you can pause and rewind me to your heart's content, and I'll see you in class.